Thank you very much. First of all, I'd like to thank organizers for the invitation. This is my first visit to Korea, and I'm enjoying so far. And so I'm supposed to talk about the connection between quantum field theory and representation theory, but I'm not a physicist, so don't ask physical questions. But maybe people in audience can answer questions. So let me start in the 3D setting. So the quantum field theory I'd like to talk about is 3D supersymmetry field theory. And I warn you, this is not rigorously mathematically defined theory. So the quantum field theory whose dimension is greater than 2 doesn't have a satisfactory mathematical definition at the moment. So I'm not going to explain what it is because I myself don't understand theory. But so this theory caught a lot of attention from mathematicians in recent years because it produces interesting mathematical objects. So one is called the Higgs branch. So if there's a theory T, you can associate to it some geometric invariant or observable. This is called Higgs branch. So H stands for Higgs. And there's another geometric invariant called the Coulomb branch. So as objects, these hyperkähler parts. So in particular, it is a symplectic variety. So mostly, in most cases, these varieties are singular. And this one is easy to define mathematically. So this one was difficult to define, but now we have a result of Biermann. But think about Nakajima, who gave a mathematical definition of Coulomb branches. So although gauge theory itself is not mathematically defined, these two objects are mathematically defined, very defined. So we can study them, and they are quite interesting symplectic varieties. But the most interesting thing is that so these two invariants are associated with one theory, that they might look totally different. However, because it comes from the same theory, you expect there are some kind of connection or a duality between. So such a duality is explained in terms of 3D mirror symmetry. which is formulated mathematically, at least in part, as a synthetic group. By Braden. So some of the statement is that the Higgs branch of one theory is isomorphic to the Coulomb branch of the mirror theory. So to check with some theory mirror to T, and the statement of symplectic duality is that there's a natural quantization of the Higgs branch. There's some quantization. So this is a non-commutative algebra. And also there's a natural quantization of Coulomb branch. And so you can talk about the representation of these algebras. And if you look at some nice category O, so they are possibility of those. So 3D gauge theory gives us interesting algebra to work with for representation theories. Hmm? 20 years. But there are other invariants other than Coulomb branch and the Higgs branch, which are algebraic objects that are defined by Gaiotto, Costello Gaiotto. That are called boundary VOAs. This is A twisted boundary. This is a B twisted boundary. So vertex. So VOA stands for vertex operator algebra or vertex algebra. So I don't know how many of you know the vertex algebra, but for now, this we can think as a generalization, certain generalization of affine category. Well, you can associate each gauge theory to of generalization of affine category. And the basic conjecture is the following. Right. So, so first of all, Higgs branch can be recovered from A twisted VOA. as associated variety of this vertex algebra. So I'll explain later that for each vertex algebra, you can associate a certain affine Poisson variety. And this Poisson variety recovers Higgs branch. And also, Coulomb branch can be recovered from E twisted VOA as associated variety. So you can think this A twisted VOA as a certain affine quantization of Higgs branch, and this one is an affine quantization of a Coulomb branch. And the second statement will be similar to the first statement of the statement over. So you can look at the A twisted VOA and also B twisted VOA of the mirror. And so what is analogous statement? So here I was not really precise. So for 3D n equal 4 gauge theory, you can, there's an ambiguity to choose to define vertex algebra. So for each, you can have a choice of boundary condition, and for each boundary condition, you can associate certain vertex algebra. And the statement is that so this vertex algebra itself may depend on the choice of boundary condition, but the category of representation should not depend on the choice of representation. So the statement is that the suitable category of module of A twisted VOA and the category of module of B twisted VOA should be derived and tensor equivalent. And there's a third statement. So Higgs, A twisted VOA is a certain, I said a certain affine quantization of Higgs branch. But in fact, this one should know Coulomb branch as well. So this should be isomorphic to the spectrum of the derived home of the vacuum. And vice versa. So each of these boundary VOA know both Higgs and Coulomb. So there are certain conditions to this statement hold. So if T is good, so there's a notion for gauge theory to be good, meaning that there's a matter field is not too small, but the representation is not too small. Then this, and anyway, so the most gauge theory are good, so we should not care about this assumption. So the point is that this vertex algebra knows both both Coulomb branch and Higgs branch. So obviously, these boundary VOA, so if you believe this conjecture are true, are better invariant than a Coulomb and Higgs branch. So we can hope that knowing these vertex algebra, we can have a better understanding of 3D mirror symmetry, which mathematician can only understand partly for the moment. Please feel free to intervene. Roughly, this quantization appears as for each vertex algebra, you can associate algebra called the Zuz algebra. So roughly this quantization. These are fine. Why did it take? Why are fine? By definition, it's a spectrum of Higgs. It's by definition, it's a fine. So it's a spectrum of some ring. So you associate some Coulomb branch Burkean equal to Burkean aspect. No, not yet, but it's open to you. Fine. But I have to warn you that this VOAs not defined or mathematicians. General, because you start with the undefined 3D, defined boundary. So our challenge is first define this vertex algebra independently somehow and study this interest. Yes. I'll explain. Yeah, so if you believe this conjecture, this gives another definition of Coulomb. So this will already tell you this object is non-trivial to define. Any other questions? So if not, let's talk about 4D thing. So now I consider another black box, which is 4D n equals to 2 superconformal field theory. So here we can also, so these have also similar to 3D setting. So just can Higgs and Coulomb branches. And known fact is that the Higgs branch of the 4D theory is the same as Higgs branch of 3D theory. So this is some 3D theory obtained from for this theory by so-called S1 reduction. So there's a way to go, way to do dimensional reduction. And the fact is that the Higgs branch remains the same. So it's, if you believe 3D mirror thing, that this should be the same as Coulomb branch of mirror theory. So in particular, this is a hypercube. But in 4D setting, so Coulomb branch, I consider Coulomb branch on R3 times S1. And then in 4D setting, Coulomb branch and Higgs branch are not symmetry. So they are not just, they are not hypercube form. So there are certain integrals. So for example, for process theory that Andrew talked about in the previous lecture, by the way, S stands for 6, because it comes from 6-dimensional theory. And in this case, it's known by Gaiotto and Moore and Andrew that this Coulomb branch is the moduli space of G Higgs bundles. On this Riemann surface. So typically, you obtain moduli space of Higgs bundle or Hitchin systems on other Coulomb surface. And there's another invariant, actually, for 4D theory, which is called the Schur index. And which is a certain Q series. So this is a certain numerical invariant. Or more often, this is a quasi-modular. So for 4D theory, so you have these three totally, maybe not totally, but the different mathematical objects that comes from 4D. But because all these three comes from one theory, you should find some duality. And the answer to this question, I think, was not clear until Beem, they all defined another invariant, which is a vertex algebra. And the fact is that the first for it, so it was constructed. So it was constructed in such a way that the character, so So this is in particular a graded vector space. And each homogeneous space is has finite dimension. So for this kind of graded vector space, you can consider Q series by just counting the dimension of the homogeneous component. And the statement is that this coincides with 0. Although we need to give some collection term like this, but this essentially this is usually called the character of the vertex algebra. So by taking character of this vertex algebra, you can recover this Schur. And more surprisingly, later it was found that the Higgs branch also obtained as the associated variety of the corresponding vertex algebra. So you can recover this from take associated. Yeah, so this is a picture by Beem and Rusty. But I think this is widely accepted in physics community. Yes?
That's if I move it to taking for
it's a good question. So you can go from 4D to 3D, and so you can ask with so this is a commutative diagram, but in general this is not commutative. But here you can, there's a choice of boundary condition. I think if you choose a appropriate boundary condition, you get the same VOA. I mean, not at least in some example, the physicists check this kind of phenomenon, but I don't know indeed. So let me state some of the property of this map. So first property is this. So in physical, so I didn't say what is, I didn't explain vertex algebra at all, but the vertex algebra appear in two-dimensional conformal field theory. So it originates in two-dimensional conformal field theory. So meaning that you can rigorously define two-dimensional chiral theory, chiral conformal field theory using a vertex algebra. So you can somehow identify vertex algebra with two-dimensional conformal field theory. And for physical theory, there's a invariant called central charge, which takes a positive value for unitary theory. So you can, in this case, you can consider two central charge. So central charge for vertex algebra and central charge of original 4D theories. And the fact is that these two numbers are related by this equation. So this means if you start with a unitary theory, which is always the case for physical theory, you end up with a non-unitary theory. So So this vertex algebra is never. So you obtain some exotic vertexes. So in particular, this is not this map to any conformal field theory to the category of VOAs. So this is not surgical. And if you look at this map, so this corresponds to the QFT. So this is kind of a dimensional reduction. So you might think it loses a lot of information for the theory, but the conjecture is that this map should be final. So meaning that the fiber is a finite set. So it's almost complete invariant, surprising. So I should remark, you can consider the same map which assign Higgs branch. But this map is not final because there are infinitely many 4D theory which have a point as Higgs branches. So this vertex algebra is a much better invariant than the Higgs branch. And also Coulomb branch, I think people expect that this map is finite.
No, I feel like,
Really? Anyway, so this seems to have this is richer than Higgs branch. And so now people expect that there should be duality between these nice invariants of the 4D. So there should be duality between Coulomb branch and the vertex operator algebras, which are called 4D mirror. So this name first appeared in the recent paper of Penshan and Xie and Wendy Yang. But this observation goes back to prediction on needs. Where they found this kind of correspondence where this is a minimal series of double algebras. So this 4D mirror symmetry is a very fascinating symmetry because unlike 3D setting, it connects different mathematical objects. So this is purely algebraic object, And this is a very nice geometric object such as Higgs bundles on Riemann's. However, the full for the mirror symmetry conjecture is not stated or formulated yet. Even in physics. So it's quite open to formulate and state and prove the 4D mirror symmetry. So what Shang Xiedan did was that they considered certain, for this theory called the Agrias-Douglas theory, whose Coulomb branch are irregular Hitching system on P1, and whose VOA is a certain representation for the admissible representation of affine Katsumudi algebra. And what they found was that there's one-to-one What they found was there's one-to-one correspondence between irreducible set of irreducible representations and the sister fixed point of the heating system in such a way that there's a monoidal structure in this category that comes from the fact that it's a representation of vertex algebra. There's certain monoidal structure coming from the fact that gives rise to representation of rational Chladnic algebra. And this correspondence is compatible with this monoidal structure. And there's also work of Beem and Fang and Yang, where they recover from vertex algebra the K part of mixed Hodge polynomial. The moduli space assuming that the P equal W conjecture. And also Shang and Yang and Zhao show that from Coulomb branch you can recover associative variety, which is the Higgs branch of the theory. So there are a lot of evidence for the mirror symmetry to exist, but the full picture is not clear yet. So I think Andrew is going to talk about story of this side for the class S theory. And I'll talk about this side of story for class S theory in later my lecture. And it's open to you to find and formulate precise coding version.
That's pretty near the frames.
Coulomb branch. So it can be Coulomb branch can be identified with
From the vertex argument, you get exact frequency.
of the cluster varieties. So this is not very topical. But again, this vertex algebra was a map is not defined for mathematicians in general. So we need to first define this vertex algebra and study the interesting property. You can predict using information of Coulomb branch. You can determine X branch by looking at Coulomb branch. Using geometry of Coulomb branch. In this case, Coulomb branch, so it fixed the point of a Coulomb branch can identify the affine spin affine, the duality.
Because how they know that it's fine. How they know that it's fine.
So why this is we believe the result of Andrew that he identified the fact that the Coulomb branch is a moduli space of Higgs branch. So this was proved by yeah. So I think Andrew is going to explain. So we can take this as a definition. And so vertex you can also define in some other way by using some mathematical imagination. And then you can try to. I'll explain examples. So in particular, you can define vertex algebra for class S theory for all cases. So now I'd like to explain this notion of associative variety or vertex algebra. So as I said, so for 3D, you have two boundary VOAs. For 4D, you have one VOA. And if you take associative variety, you recover associative variety, you recover Higgs branch. And here you will recover Coulomb branch and another Higgs branch. So this is, so for any vertex algebra you can affine for some variety. So for to define as a reduced scheme of some. So for each vertex algebra, you can define finitely generated Poisson algebra. Which is called the Zeus sheets algebra. And you just take a spectrum of this Poisson algebra. So this is actually easy to define once you have a definition of vertex algebra. But I don't want to introduce vertex algebra, at least in the first talk. So let me explain in example. So what is reduce? So as I said, vertex algebra is a generalization of affine facsimile algebra. So let's talk about the case of affine facsimile algebra. So let G be a simple E algebra, and G hat is the corresponding algebra, which is defined relation like this. And this is a normalized invariant inner product. So this is some constant multiple of killing 4, and K is central. Then you consider the following representation. So for each complex number, you define induced representation of this facsimile algebra, induced from trivial representation of this parabolic suburb. Here GT up to 0 and K up to this given level. And so by PBW theorem, this as a vector space, isomorphic. This space. And a fact is so this has a structure, natural structure of a vertex algebra, and called the universal affine vertex algebra associated with G at level A. So you can talk about the representation of this vertex algebra. And the representation of this vertex algebra is nothing but the smooth G hat module of level A. Yeah, smooth means that the XTN applied to any vector is 0 for subsample. Zero. Label K means K actors K, small k. So you can think this vertex algebra as kind of a universal enveloping algebra of Katsumudi because representation of theory is the same. And so if you consider unique simple graded portion of this one. So this is a irreducible representation of Katsumudi. This inherits vertex algebra structure from this universal one. And this is called a simple affine vertex algebra or a vacuum representation of G hat. So in particular, you can talk about the representation of this vertex algebra, and with this form a certain full subcategory of KG module, which is identified with a category of smooth representation of G hat. And we are mainly interested in this category. So this depends on K, and depending on K, this has a very nice structure. Depending on K. Well, which category? Well, it depends on which category you take, but mostly they have monoid. Sorry?
Did you need to say for generic K, this is for the category, but otherwise not?
So the category of at least ordinary representation of the moment. Ordinary means the module you can where characters are really. But you can also consider category all smooth representation. This is a bit difficult to define. So it really depends which category.
So it's technically, we do expect.
Yes, it's a technical. So for this kind of so to define associative variety, I just define after defining the six algebra. And as a vector space, this is very easy, right? So this is just a quotient space of V by this subspace. So you forget about anything which belongs here. So because V is a quotient of U G minus. From this, if there's a, you find that there's a surjection from symmetric algebra of G to here, which sends this kind of monomial to the zero is the highest weight vector, the image of this vector, because you forget anything. This minus one. And so this one can be identified as a polynomial function. This is a Poisson algebra by the Euler of Poisson structure, which comes from the Lie bracket. And the fact is that this is a Poisson algebra. So if you write this as a quotient, so there's some Poisson ideal. Which gives this kind of isomorphism. And so the associative variety in this case is just a zero locus of this idea. This is very easy to define, but it's quite complicated, difficult to compute. And if V is VKG by PBW theorem, so this map is isomorphism. There's no kernel, which means associative variety for the universal one is just a G star. So if K is generic, meaning it's not rational, then this universal one is already irreducible. So this means the associative variety is the whole G star. There's another other extreme cases. So now that the associative variety is a point, if and only if this one is integrable representation of E hat, and this happens if and only if K is non-negative. Okay. So the associative variety, zero associated variety condition characterizes integrability condition. And you cannot really define integrability for arbitrary vertex algebra, but this kind of definition that we extend to arbitrary vertex algebra. So you can use this zero associated variety condition to define a finiteness property of vertex. But so certainly integrable representation of G hat nicest representation of paternity algebra. However, we are interested in the vertex algebra coming from 4D or 3D, but this never integrable vacuum representation never appear from 4D because it is unitarily. So if you want to find some interesting vacuum representation that comes from 4D, you have to look at more wilder representation of Katsumori algebras. And so maybe from tomorrow, I try to present some example. Hmm? Yeah. Never. Yes. Yeah, so I stop here today, and from tomorrow I'll explain example.